In the last video we looked at how we can split forces up into components in two perpendicular directions. This is particularly important when we are working with forces acting on particles which lie on an inclined plane. So in this video we're going to look at the process of splitting forces into components when those forces are acting on inclined planes. So when we've got motion on an inclined plane, it's usual to split the forces into components that are parallel to the inclined plane and perpendicular to the inclined plane. So for a first example, let's suppose we've got a particle of weight W newtons is pulled up a rough plane inclined at 17 degrees to the horizontal by a string making an angle of 30 degrees with the horizontal. We're going to draw a diagram to show all the forces acting on the particle, and then we're going to find the components of each of these forces in directions that are parallel to and perpendicular to the inclined plane. Well, the forces acting are going to be the weight of the particle, the normal reaction of the particle with the plane, the frictional force opposing the motion of the particle up the plane, and the tension in the string pulling the particle up the plane. So there would be a representation of the forces acting on our particle. So what we've got to do in this is we've got to split each of the forces up into the components along the plane and perpendicular to the plane. The weight can be split reasonably easily by creating a right-angled triangle whose hypotenuse is the weight and whose other two sides are parallel and perpendicular to the plane. Now, if we use a little bit of trigonometry, or a little bit of geometry rather, we can see that the angle alpha must be 180, take away 90, take away 17. In other words, the angle alpha must be 73 degrees. And because the component of the weight into the plane will be at right angles to the plane, we've got alpha plus beta must equal 90 degrees, so the angle beta must be 17 degrees. Once we've done that, we can see that the component of W into the plane is the adjacent side of the triangle to the angle beta. So we can say that the component of W into the plane is W cos 17, and the component of W down the plane is the opposite side, and that therefore is going to be W sin 17. Moving now to the normal reaction, N, and that acts perpendicular to the plane, so we can immediately write down that the component of N out of the plane is equal to N, and the component of N down the plane or up the plane is equal to 0. Considering next the frictional force, well, we know the frictional force acts down the plane, so we can immediately write that the component of F out of the plane must be equal to 0, and the component of F down the plane is just equal to F. The components of T need a little bit more work, and in order to do that, what we need to do is we need to draw a triangle again, in which T is the hypotenuse and the other two sides of the triangle must be parallel to and perpendicular to the direction of the plane. Again, a little bit of elementary geometry gives me the angle between T and the direction of the inclined plane is 13 degrees. So we can see that the component of T out of the plane is the opposite side of our triangle to the 13 degrees. So that is going to be of size T sine 13. And the component of T up the plane is going to be the adjacent side of our triangle. And it's the side which is adjacent to the angle of 13 degrees. So that is going to have size T cos 13. Now we'll look at a second example. So the diagram shows the forces acting on a particle of weight 10 newtons placed on an inclined plane. We're told that the total force, or the net force, acting perpendicular to the slope is 0. And what we've got to do is we've got to find the value of the force P, and we've got to find the magnitude and direction of the resultant force. So let's start by considering each of the forces and resolving each of the forces in directions that are parallel and perpendicular to the inclined plane. So we're going to take our x direction as being up the plane and our y direction as being out of the plane. So first of all, if we look at the weight, then we can see from our little triangle that we've drawn there that the angle between the weight of 10 newtons and the direction going into the plane is 23 degrees. So the component of the weight parallel to the plane is the opposite side to that, at 23 degrees, so that must be 10 sine 23, and that is acting down the plane. The component of perpendicular to the plane is the adjacent side to the 23 degrees, so that is going to be 10 cos 23 into the plane. For the force of P acting out of the plane, well, the component parallel to the plane is 0 because P is acting perpendicular to the plane. The component perpendicular to the plane is P out of the plane. Moving on to the 5 Newton force. The 5 Newton force is acting down the plane, so the component parallel to the plane is 5 newtons down the plane, and the component perpendicular to the plane is 0 because it doesn't act at all perpendicular to the plane. And then finally, for the 15 Newton force, 15 Newton force is making an angle of 10 degrees with the plane, so it has a component of 15 cos 10 up the plane and a component of 15 sine 10 out of the plane. Now we're told that the net force, or the total force acting perpendicular to the slope, is 0, and we've got to find the value of P and the magnitude and direction of the resultant force. So if we take the total of the x components of the forces, so that's the components of the forces along the plane, then we've got a force of minus 10 sine 23 being the component of the weight down the plane, and because the positive direction for x is up the plane, the component of the weight is down the plane, so must be negative. So we've got minus 10 sine 23. The force P has no component up or down the plane. The 5 Newton force is equivalent to a force of 5 newtons down the plane. In other words, its x component is minus 5 because the positive direction for x is up the plane. So the x component of the frictional force there of 5 newtons is going to be minus 5. And then finally we've got the x component of the 15 Newton force is 15 cos 10 up the plane, so that is positive 15 cos 10. So the total of all of the x components is equal to 5.864 newtons. Doing the same now for the components perpendicular to the plane, and in this case remember out of the plane is the positive direction for y, into the plane is in the negative direction for y. So the total of the y components of the forces, first of all we've got 10 cos 23 into the plane, in other words minus 10 cos 23 is the component of the weight in the y direction. We've got then for P has a component of P out of the plane, so that's plus P. The 5 Newton force has no component in the y direction, and the 15 Newton force has a component out of the plane of size 15 sine 10. So the y component is plus 15 sine 10. And that simplifies to P minus 6.60. But we were told in the question that the total force, the net force, acting perpendicular to the slope is 0. So we're being told that P minus 6.60 must equal 0. So the force P must have magnitude 6.60 newtons, and the magnitude and direction of the resultant force is simply a force of size 5.864 newtons acting up the plane. We'll be coming back to inclined plane problems quite a bit in subsequent videos.